Imagine going to the doctor, right, with this just incredibly stubborn, agonizing knot in your back.
Oh, yeah. We've all been there.
Right. You know the exact one. It sits right there under your shoulder blade, and it feels like a literal pebble under your skin.
Just completely locked up.
Exactly. And instead of giving you a massage or, telling you to stretch more, the doctor points to an ultrasound screen and tells you that you have accidentally built a battery in your shoulder and it is currently electrocuting your nerves.
I mean, it sounds completely like science fiction, right?
It really does.
But as we are learning today, it is incredibly real biophysics.
Yeah, so today we are looking at the groundbreaking physics of why your chronic physical tension, your stiffness, or just your unexplained pain might actually be a trapped electrical field.
Because for decades, the medical field thought they knew exactly why you get those knots.
Right.
And they thought they knew exactly why those knots twitch when a physical therapist or a doctor needles them.
Yeah. But a new framework called the fascial capacitor model is basically turning that old understanding completely upside down.
Okay, let's unpack this. We are going to explore how your body's connective tissue isn't just, inert wrapping paper for your muscles. It literally transforms into an electrical capacitor.
Yeah, and we are basing our exploration today primarily on a highly detailed 2026 preprint paper. It's by researchers Hiroaki Kimura and Tadashi Kobayashi.
It is dense.
Oh, extremely does. They have synthesized just a massive amount of supporting research spanning anatomy, quantum biology, and biomechanics.
Which is quite the combo.
It really is. And what they are proposing is a fundamental shift from viewing the body purely as this, mechanical system of levers and pulleys to viewing it as a complex bioelectrical grid.
Right.
It involves piezoelectricity, cellular biology, and how mechanical stress in your body is physically converted into trapped electrical energy.
Yeah, and when I was poring over these sources, the visualization that kept coming to my mind was a twisted copper wire.
Okay, yeah, I like that. Like, if you have a pristine straight wire, energy flows through it perfectly, right?
Exactly.
But if you take that wire and crush it or bend it or kink it, the flow is disrupted. The energy just gets trapped.
Yeah.
And today we are going to examine the precise physics of how your body's fascia becomes that kinked wire. Like how an electrical charge builds up to agonize your nervous system and how something as simple as a medical needle can act as a bridge to basically short circuit that trapped energy and give you instant relief.
And the path we're going to take through this research is really a journey of scientific evolution. I mean, we need to start with the established dogma.
The old way of thinking.
Exactly.
Yeah.
What doctors have confidently believed for the last 50 years about muscle twitches and trigger points.
Right.
From there, we have to look at a glaring anomaly that recently just blew that theory wide open.
The plot twist, yeah.
Then we will explore the physics of how healthy, fluid tissue transforms into a rigid electrical insulator. Detail the converging independent lines of scientific research that prove this is happening, and finally reveal how this redefines the treatment of pain for you.
So let's start with the mystery of that twitch.
Let's do it.
Because if you have ever had dry needling or a trigger point injection, you might have experienced this firsthand. The practitioner hits that exact tender spot and suddenly, bam,
Yep, the jump.
your muscle does this massive involuntary jump. In the literature, they call it the local twitch response, or LTR.
Right.
So what was the traditional view here? Like, if I went to medical school 10 years ago and asked my professor what causes that jump, what would be the textbook answer?
So the textbook answer would be the Travel, Simons, and Hung framework.
Okay.
This has been the absolute bedrock of myofascial pain treatment for over half a century.
Wow, so a long time.
Oh, yeah. Back in the late 20th century, Dr. Janet Travlin, who many people actually know as President John F. Kennedy's personal physician.
Oh, I didn't know that.
Yeah. She, along with Dr. David Simons, pioneered the comprehensive mapping of myofascial pain syndrome.
Okay.
They, and later researchers like C.Z. Hong, built what we call the integrated trigger point hypothesis.
Okay, so when we talk about a trigger point in this classical sense, what is actually happening on a microscopic level? Because, we all use the phrase muscle knot, but muscles don't actually tie themselves into literal knots.
Right, they definitely don't. The classical theory centers entirely on a microscopic structure called the motor end plate.
The motor end plate.
Yes. Think of the motor end plate as the highly specialized docking station where a motor nerve fiber physically interfaces with a muscle fiber.
Okay.
It is the command center. So when your brain wants a muscle to contract, an electrical signal travels down the nerve.
Makes sense.
And when it reaches the motor end plate, The nerve releases a chemical neurotransmitter called acetylcholine across a tiny gap into the muscle tissue.
Ah, acetylcholine.
Right. Exactly. The muscle receptors catch that acetylcholine, which triggers a wave of depolarization in the muscle fiber, causing it to contract.
So it's basically an electrochemical relay. Electricity becomes a chemical, which then becomes a physical movement.
Exactly. That's the perfect way to phrase it. Now, the traditional Travel and Simons theory argued that in a trigger point, something damages these motor end plates.
Okay, so they break.
Yeah, they become profoundly dysfunctional. Instead of releasing acetylcholine only when commanded by the brain, these damaged end plates start leaking it continuously.
Oh, so the nerve is just dripping this contraction chemical onto the muscle fiber 24/7.
That is the idea. This persistent chemical leak causes continuous, spontaneous electrical activity in that specific region.
Wow.
It keeps a tiny, microscopic segment of the muscle fiber locked in a state of permanent contraction, forming what they call a taut band.
So that taut band is what you feel is the knot.
Exactly. That is the classical knot.
Okay, so if that's the knot, then how did they explain the twitch when someone sticks a needle into it?
Well, the conventional wisdom assumed that when a doctor or physical therapist inserts a needle and elicits that massive local twitch response, the needle is physically striking and disrupting this cluster of dysfunctional motor end plates deep within the muscle belly.
Oh, I see.
The physical trauma of the needle hitting the nerve ending forces a massive, sudden depolarization. The muscle fiber twitches violently, and somehow, and this was always a bit vague, that violent reset stops the chemical leak, allowing the taut band to finally relax.
I mean, I have to admit, that sounds incredibly logical.
Right.
You have a malfunctioning nerve-muscle connection, you physically disrupt it with the needle, it fires all at once and resets. It's like unplugging a frozen router and plugging it back in.
It makes perfect intuitive sense, which is exactly why it stood as the accepted truth for decades. And crucially, it seemed to fit the data they had at the time.
What data?
Well, when researchers took specialized electromyography needles, which act like tiny microphones for electricity, and inserted them into these painful spots, they did record spontaneous electrical activity.
Okay, so they heard the noise.
Exactly. They could see the electrical noise on their monitors.
No.
Because they were poking into a muscle and they saw electrical noise, they logically assumed that noise had to be coming from the motor end plates of the muscle fibers.
But wait, this brings us to the anomaly that Kimura and Kobayashi highlight in their paper. And this is where the story gets really fascinating, because technology finally caught up to the theory. We aren't just relying on feeling for a knot with our fingers anymore, right?
Precisely. We now have high-resolution ultrasound. We can look inside the tissue in real time, down to the millimeter, while a procedure is actually happening. And this changes absolutely everything.
Yeah, so the paper references a massive clinical video archive from researchers looking at ultrasound-guided fascial hydrorelease procedures.
Yep.
They went back and analyzed 89 perfectly documented cases of the local twitch response.
89 cases.
Right. They watched the screen to see exactly where the tip of the needle was, the precise moment the muscle twitched. Out of those 89 twitches, how many occurred at the motor end plate inside the muscle?
0. Not a single one.
Wait, literally 0?
0. 100% of the documented twitches occurred completely away from the motor end plates.
That is insane. So where were they happening?
They happened in a distinct type of connective tissue that Kimura and Kobayashi refer to as stacking fascia.
Stacking fascia.
Right. They observed the twitch happening when the needle pierced the intermuscular fascia, the thick layers separating different muscle groups.
Okay.
Or the perineural fascia, which is the sheath wrapping around nerves like the sciatic nerve, or even in ligaments. These are anatomical locations where motor end plates literally do not exist.
But hold on, if 100% of these twitches are happening in connective tissue where there are no motor end plates to trigger, how did the entire medical community get this wrong for half a century?
It's a great question.
I mean, that isn't just a minor statistical error. That implies they were looking at an entirely different phenomenon.
It comes down to the limitations of historical tools, honestly, and the danger of foundational assumptions. Remember, 50 years ago, they were inserting needles blindly.
Right, just by feel.
Exactly.
Yeah.
They palpated the skin, felt a hard lump, pushed a needle in, and saw a twitch. Because the lump was inside the border of a muscle, they assumed the needle was stimulating the muscle tissue itself.
Because, I mean, what else could it be? Connective tissue, the fascia? was just considered inert wrapping paper, right? It just held the meat together. It wasn't supposed to actually do anything active.
Exactly. Fascia was literally the stuff anatomists used to scrape away and throw in the trash so they could look at the important stuff like muscles and organs.
Yeah.
But with high-resolution ultrasound, we can see the needle tip piercing the tissue layers like a ship moving through water. What they observed was that the twitch did not happen when the needle was deep inside the fleshy belly of the muscle. The twitch occurred the exact millisecond. The conductive needle tip pierced the dense, thickened layers of fascia between the muscles or covering the muscles.
The wrapping paper.
The wrapping paper is where the action is. The doctors of the past were observing the correct physiological response, the twitch, the electrical noise on their instruments, the subsequent pain relief, but they were attributing it to the wrong biological mechanism and the completely wrong anatomical structure.
Just because their flashlight wasn't bright enough to see what the needle was actually touching?
Precisely.
That is a massive paradigm shift. It's like hearing a rattling noise in your car engine, and for 50 years mechanics have been rebuilding the transmission, only for someone to finally buy a brighter flashlight and realize a piece of plastic was just vibrating against a fan belt.
That's a perfect analogy. It completely reorients the problem.
But if the twitch isn't coming from the motor end plate leaking acetylcholine, we really need to understand what is actually happening in the stacking fascia, what is making it twitch, and why does it hurt in the first place?
Right. To understand stacking fascia, we have to contrast it with healthy fascia. We need to look at the biophysics of what connective tissue is actually made of and how it behaves when you are pain-free versus when you are in chronic pain.
Let's do that. Let's break down the physics of healthy tissue. If I have perfect posture, no injuries, no pain, what is going on inside my deep fascia right now?
So your deep fascia is an incredibly complex, highly organized, dynamic web. Structurally, it is built somewhat like a sandwich.
Okay, sandwich.
You have these sublayers of densely packed protein fibers, specifically type I collagens.
Collagen, right.
Collagen is highly structural. It provides tensile strength. But between these dense collagen layers, you have a looser gel-like layer called the ground substance.
And what is in this ground substance that makes it gel-like?
It is heavily populated by a complex molecule called hyaluronic acid, or HA, along with just an abundance of highly structured water.
Wait, hyaluronic acid, I feel like I see that on every skincare bottle at the pharmacy. It's used for moisturizing, right?
Yes, exactly. Because its defining characteristic is its ability to bind and hold massive amounts of water.
Okay.
In your fascia, healthy hyaluronic acid acts as a profoundly slippery, fluid lubricant. Think of it like a high-grade synthetic motor oil.
I see.
It allows the dense, fibrous collagen layers to glide smoothly and independently over one another whenever you move a muscle, bend a joint, or take a breath.
Okay, so healthy fascia has collagen for structure and a fluid HA gel for glide. Where does the electricity come in? I thought this was a battery.
This is where we introduce the concept of piezoelectricity.
Piezoelectricity?
Yeah. The word piezo comes from the Greek word meaning to press, squeeze, or deform. Certain materials in nature have a crystalline structure that generates an electrical charge when you apply physical mechanical force to them.
Oh, like the quartz crystal in a wristwatch. The battery applies an electrical charge to make it vibrate to keep time. Or, conversely, if you hit a piece of quartz with a hammer, it generates a spark of electricity.
That is the exact mechanism.
Yeah.
Well, the type I collagen in your fascia is heavily piezoelectric.
Yeah.
Yes. Every single time you move your body, you are stretching, compressing, and deforming those collagen fibers. And every time you do, they generate a tiny, localized electrical charge.
Wow.
You are literally generating electricity with every step, every breath, and every heartbeat.
That sounds like it could build up and shock me. Why doesn't healthy fascia trap all this electricity?
Because of the state of the hyaluronic acid in that healthy ground substance.
The motor oil.
Exactly.
Mm-hmm.
In a healthy state, that HA layer is highly hydrated. It is filled with fluid. And fluid, especially biological fluid rich in ions, is highly conductive.
Okay.
So the collagen generates an electrical charge, but it immediately encounters this conductive fluid layer.
It's like dropping a pebble into a fast-moving river. The ripple is created, but the current dissipates it instantly.
That's a great way to look at it. In physics terms, we measure how fast a system dissipates charge using something called the RC time constant, the resistance capacitance time constant.
The RC time constant.
Right. In healthy fascial tissue, the RC time constant is in the nanoseconds. The tissue is what we call a nanosecond dissipator. The electrical charge is generated by mechanical movement, and it disperses harmlessly through the tissue network faster than you could ever measure. The tissue does not store energy.
So fluid tissue is conductive tissue, but obviously we don't always stay perfectly healthy. What happens when I spend 10 hours a day hunched over a laptop, or I play tennis every weekend with this terrible form, or I get into a minor car accident? How does this beautiful, gliding, dissipating system break down?
Chronic mechanical stress or acute trauma changes the cellular environment. Deep within the fascial layers, you have specialized cells called fasciocytes.
Astrocytes, okay.
Their primary job is to manufacture and secrete that hyaluronic acid to keep everything lubricated.
Right.
When you subject your body to chronic abnormal mechanical load, like awful posture at a desk, these fasciocytes sense the stress. They try to protect the tissue by going into overdrive. They start pumping out excessive amounts of hyaluronic acid.
They overproduce the lubricant, which, I mean, sounds like a good thing, right? More glide?
It would be if the HA stayed fluid. But when there is a massive overproduction of hyaluronic acid in a localized area, the molecules begin to hyperaggregate.
Hyperaggregate, meaning they clump up.
Exactly. They tangle and clump together into massive chains. As they hyperaggregate, they physically squeeze the water out of the ground sections. The environment becomes dehydrated.
So instead of fresh, slippery motor oil, what do we have?
You have sludge.
Yeah.
Imagine leaving a car sitting out in freezing temperatures with dirty oil. It loses its viscosity. It becomes thick, sticky, and highly densified.
Wow.
This is what the paper refers to as stacking fascia. The layers of fascia get glued together by this sludgy HA. They lose their ability to glide independently, which is exactly why you feel physically stiff and restricted.
Okay, I can visualize that perfectly. The mechanical glide is ruined. But Kimura and Kobayashi are talking about electricity. How does this sticky sludge relate to the capacitor model?
This is the core biophysical shift that changes everything. When hyaluronic acid hyperaggregates, loses its water, and turns into dense sludge, it undergoes a profound phase transition.
A phase transition.
Yes, it doesn't just change mechanically, it changes electrically. It loses its conductivity and becomes a dielectric.
A dielectric. Wait, you mean an electrical insulator?
Yes, exactly. It becomes a highly effective barrier to electrical flow. Think about what this means structurally.
Okay.
You now have a layer of conductive collagen, a thick insulating layer of sludgy HA, and another layer of conductive collagen. You have inadvertently built a multi-layer ceramic capacitor, an MLCC, right inside your tissue. This is the exact architectural design electrical engineers use when they want to store an electrical charge on a circuit board.
I am literally building microscopic batteries in my back because of bad posture.
You are. And remember those piezoelectric collagen fibers?
Yeah.
You are still breathing. Your heart is still beating. Your arteries are still pulsing. You are still making micro movements. You are constantly generating electrical charge.
But now the river is frozen.
Exactly. The river is frozen solid.
Yeah.
The conductive pathway is blocked by the dielectric HA sludge. The nanosecond dissipator is gone.
So the electrical energy has nowhere to go. It just gets trapped in the capacitor.
The rate at which your body generates electricity now exceeds the rate at which it can dissipate it. The charge accumulates, building a localized, trapped electrical field.
This is a brilliant transition into the actual mechanism of pain, because if I'm trying to wrap my head around this from a top-down view, how do we get from a desk job to screaming nerve pain? The authors outline a very specific 5-stage cascade.
Yes, they do.
Walk me through this, step by step, as if I need to explain it to a student. What is stage 1?
Stage 1 is stacking formation. This is the mechanical beginning. Chronic stress, repetitive overload, or postural dysfunction stimulates the fasciocytes. They overproduce HA. The HA hyperaggregates, pushes out the water, and the fascial layers become physically thick, glued together, and densified. The oil turns to sludge.
Got it. Stage 1, the tissue gets sticky and densified. What's stage 2?
Stage 2 is capacitor formation. This is the electrical consequence of stage 1. Because the water is gone, that densified HA layer becomes a dielectric insulator. Structurally, the alternating layers of dense collagen and sludgy HA now form a functional biological capacitor capable of storing electrical energy.
Stage 2, the battery's built. Stage 3.
Stage 3 is charge accumulation. Life continues. You move, you breathe. Mechanical deformation of the collagen continually generates small piezoelectric charges. Because the dielectric HA prevents dissipation, this electrical energy becomes trapped. A steady-state electrical field begins to build and pool within that fascial sandwich.
Okay, so I have a trapped pocket of electricity. Here's where it gets really interesting, because I have static electricity in my hair in the winter, and it doesn't hurt until I touch a doorknob and get shocked. Why does this trapped field equal pain? What is stage 4?
Stage 4 is multimodal afferent activation.
Multimodal afferent.
And this is where the nervous system is forced into the picture. Your deep fascia isn't just collagen and HA, it is intensely innervated. It is packed with microscopic sensory nerves called afferent-free nerve endings. Their job is to report the status of the tissue back to your brain.
And they are sitting right in the middle of this newly formed battery.
Exactly. And they are being attacked on multiple fronts simultaneously. That is what multimodal means. First, they're being subjected to that trapped electrical field. This constant voltage directly acts on the voltage-sensitive ion channels of the nerve, depolarizing them and causing them to fire indiscriminately.
So the nerve is essentially being constantly electrocuted by the trapped charge.
Yes, but that isn't all. Because the tissue is now sludgy and stiff, the mechanical tension is physically pulling on the nerve membrane. The nerves in your fascia have specialized molecular doors called PO1 and piezo2 channels.
Piezo 1 and piezo 2.
These are mechanically gated channels. They don't care about electricity. They open when the cell membrane is physically stretched. So the stiffness is ripping open these doors, flooding the nerve with calcium and forcing it to fire.
Wow. It's being chemically smothered by the sludge, mechanically stretched by the stiffness, and electrically zapped by the capacitor all at the exact same time. It's a sensory nightmare.
It's an absolute sensory nightmare, which inevitably triggers stage 5, the positive feedback loop.
The downward spiral.
Precisely. These highly agitated nerves are screaming at your spinal cord, sending a flood of pain signals.
Yeah.
And how does your body naturally respond to severe localized pain? It guards. You stop moving that area. The surrounding muscles tighten up in a protective spasm.
And by not moving, I am reducing blood flow to the area.
You create localized ischemia, a lack of oxygen and fresh blood. The lack of movement and lack of fluid exchange means the tissue gets even more dehydrated. The fasciocytes sense this distress and pump out even more HA, which creates more sludge, thickening the dielectric insulator, trapping more electricity, which causes more nerve activation.
Oh, man.
The capacitor grows, the pain intensifies, and the cycle becomes totally self-sustaining.
That is the complete path to chronic pain. Stacking formation, capacitor formation, charge accumulation, nerve activation, and the positive feedback loop. It explains so perfectly why just, stretching a tight muscle rarely cures chronic pain. You aren't just fighting short muscle fibers, you are fighting an active, self-sustaining electrical field embedded in a dehydrated gel.
It explains the chronicity and the stubbornness of these conditions in a way the old motor end plate theory never could.
Now, I want to explore the foundation of this because this is where my mind was truly blown reading the source material. The authors, Kimura and Kobayashi, they didn't just invent this capacitor idea out of thin air while staring at a whiteboard, right? This isn't a fringe theory based on a single speculative paper.
No, it is the exact opposite. A robust biological theory shouldn't require you to invent new physics. It should take established, peer-reviewed facts and reveal how they connect. The fascial capacitor model is built upon the convergence of 8 entirely independent lines of scientific research developed by different teams across the globe over the last 70 years.
I want to spend significant time unpacking these 8 pillars, because when you see how fields ranging from quantum physics to molecular genetics unknowingly solve different pieces of the same puzzle, it is staggering. Let's start with the first one. How far back does this go?
It goes back to the 1950s in Japan, with 2 researchers named Fukada and Yasuda.
The 50s.
Yeah. They are the grandfathers of biological piezoelectricity. At the time, physicists knew that certain crystals generated electricity when squeezed. But Fukada and Yasuda were the first to rigorously prove that biological tissues possess this exact same property.
Wow.
They initially demonstrated it in bone, showing that mechanical stress on a bone generates an electrical field that guides bone remodeling.
Wait. Wolff's Law, the idea that bone grows stronger under stress, they found the electrical mechanism behind it.
Exactly. But they quickly expanded their research to soft tissue, specifically collagen. They proved that macroscopic collagen, the primary protein in our fascia, generates measurable electrical currents when subjected to mechanical deformation. This established the foundational premise: the human body can generate its own structural electricity.
Okay, so pillar 1, the macroscopic discovery of collagen piezoelectricity in the 50s. What is pillar 2?
Pillar 2 brings us into the modern era of nanotechnology. A team of researchers, Minori Jo Landon and Yu, they wanted to know if this electricity was just a bulk tissue phenomenon or if it went deeper. They utilized a highly advanced tool called atomic force microscopy.
What is atomic force microscopy? How is that different from just looking through a really powerful glass microscope?
An atomic force microscope doesn't use lenses or light to see. It is more akin to a blind person reading Braille.
Oh, that's interesting.
Yeah, it uses an ultrafine microscopic cantilever with a tip that is only a few nanometers wide. This tip physically traces the surface of an object, feeling its topography at the molecular level.
So they're literally feeling the individual molecules of collagen.
Yes, and they use this tool to measure the electrical potential of a single, isolated collagen fibril while applying microscopic force. They proved that the piezoelectric effect isn't just some artifact of large tissue bundles. It is a fundamental, quantum-level property inherent to the molecular structure of the collagen protein itself.
That is mind-blowing.
Every single nanometer of collagen in your body is an independent electromechanical generator.
That is incredible. Pillar 2, nanoscale proof of piezoelectricity. Where does Pillar 3 come from?
Pillar 3 comes from the Grodzinski Research Group at MIT. While others were looking at the solid collagen, the MIT group was studying the fluid environment, the cartilage and connective tissue ground substance. They proved the existence of something called streaming potentials.
Streaming potentials, what does that mean?
It means that you don't even need to stretch the collagen to generate electricity. The ground substance is a charged matrix. Grodzinski's team proved that simply forcing fluid to flow through this charged matrix generates millivolt range electricity.
So even if I am not doing heavy mechanical lifting to stretch my fascia, just the act of fluid moving around inside the tissue generates a voltage.
Precisely. Between the stretching of the collagen and the movement of the fluid, the tissue is an incredibly active electrical environment.
Okay, pillar 4. We have the physics, now we need the anatomy.
Pillar 4 is the groundbreaking work by the Stecco family and their research group at the University of Padova in Italy. Historically, fascia was ignored by anatomists. The Stecco group painstakingly mapped the fascial web, but their most critical contribution to this model was cellular. They discovered the fasciocyte.
The cell we talked about earlier that acts as the manufacturing plant for hyaluronic acid.
Yes, they identified it, isolated it, and studied its behavior. Furthermore, the Stecco group was the first to draw a hard biological distinction between two very different tissue states, fibrosis and densification.
Break that down for me because those sound like the exact same thing, just tough, scarred tissue.
They're completely different. Fibrosis is a structural ulceration. It involves excessive deposition of collagen fibers, usually following severe trauma or surgery. It is irreversible scarring. The architecture of the tissue is permanently changed. Densification, on the other hand, does not alter the collagen architecture. It is purely the hyperaggregation of hyaluronic acid. The HA turns to sludge.
And because it's just thick and fluid, it can be reversed.
Exactly. The Stecco group proved that this reversible densification of HA is the primary driver of nonspecific myofascial pain. They provided the anatomical substrate for the capacitor's dielectric layer.
That is a crucial piece of the puzzle. The sludge is real, it has a name, and it has a source. Pillar 5 moves us into genetics, right? You mentioned YAP and TAZ earlier.
Yes. Pillar 5 comes from the DuPont and Piccolo Research Group, also out of Padova. They solved one of the greatest mysteries in cellular biology, mechanotransduction.
Mechanotransduction.
How does a cell, which has no eyes or ears, know that the tissue around it is stiff? And how does it translate that physical stiffness into a chemical command to change its behavior?
Right. How does a physical pull change cellular DNA? That sounds impossible.
It's mechanical linkage. Cells have an internal skeleton made of actin filaments. This internal skeleton connects to the outside environment through proteins called integrins that span the cell membrane. DuPont and Piccolo discovered two specific proteins inside the cell named YAP and TAZ. When the extracellular matrix becomes sludgy and stiff like in our stacking fascia, that stiffness pulls on the integrins.
The outside sludge literally yanks on the cell's membrane.
It yanks on the integrins, which pull the internal actin skeleton, which physically stretches the nucleus of the cell. This mechanical stretching opens the pores of the nucleus water, allowing the YAP and TAZ proteins to squeeze inside.
Wow.
Once inside the nucleus, they bind to the DNA and literally change which genes are turned on.
They act as genetic switches.
Yes, they instruct the cell to adapt to the stiff environment by producing more stiffening agents. It is how the tissue chemically remembers to stay stiff, locking in the chronicity.
Wow. So the physical sludge pulls on the cell, forcing proteins into the nucleus to turn on the blueprint to make more sludge. That is an incredibly insidious loop. Pillar 6.
Pillar 6 is Nobel Prize-winning research.
Oh.
In 2021, the Nobel Prize in Physiology or Medicine went to Artem Patapushin and David Julius, in part for Patapushin's discovery of the piezo-1 and piezo-2 channels.
The doors.
Yes. For decades, neuroscientists knew nerves fired based on chemical neurotransmitters or electrical voltage. But Patapushin's team at Scripps Research discovered these massive, complex protein structures embedded in cell membranes that act purely as mechanical sensors.
These are the mechanical doors we talked about in stage 4?
Yes, they resemble tiny propellers or levers. They don't care about chemicals or voltage. They open strictly when the cell membrane is physically stretched or deformed by tension. This proved unequivocally that your nerves have dedicated hardware to sense the physical stiffness of the fascial sludge, and that mechanical tension alone is enough to trigger severe pain signaling.
The puzzle pieces are just snapping together perfectly. Pillar 7.
Pillar 7 comes from Dr. Helene Langevin and her research group at Harvard and the NIH. For years, she has studied the connective tissue continuum. She utilized ultrasound and cellular analysis to prove that the fascial web acts as a real-time, body-wide mechanical signaling medium.
What does a body-wide mechanical signaling medium actually look like in practice?
Her team demonstrated that when you apply a mechanical stretch to tissue, for example, by inserting an acupuncture needle and gently rotating it so the collagen fibers wind around the needle,
Right.
the fibroblasts in the connective tissue don't just react locally. The mechanical signal propagates outward. Cells millimeters or even centimeters away sense the pull and physically reorganize their internal cytoskeletons in response. She proved the fascial web is an interconnected communication network.
Like a spider web. You pluck one strand in the corner, and the spider sitting in the center feels the exact vibration instantly.
Exactly.
And finally, Pillar 8.
Pillar 8 provides the final anatomical verification. Recently published in the International Journal of Molecular Sciences, researchers Fede, Piri, and their colleagues conducted an exhaustive histological mapping of the deep fascia.
Okay.
They verified the precise molecular biology and documented the intense, localized nerve density embedded within these connective tissue layers. They proved that the anatomical hardware, the dense clusters of afferent-free nerve endings, exist exactly where the capacitor model predicts it should be.
I mean, when you lay all 8 pillars out like that, it is overwhelming.
Yep.
You have Japanese physicists in the 50s finding the electricity, nanoscientists measuring the fibrils, MIT mapping the fluid voltage, Italian anatomists finding the HA cells, geneticists discovering the mechanical DNA switches, Nobel laureates finding the physical nerve doors, Harvard mapping the body-wide web, and modern histologists confirming the nerve density. None of them were trying to solve the puzzle of the local twitch response. They were just doing fundamental science.
And Kimura and Kobayashi simply looked at all 8 of these established undeniable facts and realized they form a single cohesive engine. The fascial capacitor model isn't asking you to take a leap of faith. It is just asking you to look at the synthesis of a century of science.
It is brilliant. However, I know from reading the literature that not everyone is on board yet. Whenever you propose a grand unified theory that upends 50 years of medical dogma, somebody with a calculator is going to try to punch a hole in it. Let's explore the pushback. What is the primary argument the skeptics use to dismiss this electrical model?
The primary counterargument is rooted in mathematics and neurophysiology. It is entirely valid if you only look at the numbers superficially.
Okay, what's the argument?
The skeptics look at the capacitor model and say, okay, you claim this built-up electrical charge discharges when needled, and that discharge is what triggers the nerve to fire, causing the muscle twitch. But we know the threshold required to trigger a thick alpha motor neuron is a voltage spike of roughly 15 to 20 millivolts.
So 15 to 20 millivolts is the absolute floor to start the engine?
Correct. But then the skeptics calculate the maximum possible capacitance of a fascial layer. Based on the volume of collagen and HA, they find that the steady-state bulk voltage of this tissue is only about 0.4 millivolts at rest.
Oh.
Even if you apply sudden pressure during a needle injection, the theoretical spike might reach 25 millivolts spread across the entire tissue area. The skeptics argue that a baseline of 0.4 millivolts and a messy transient spike of 25 millivolts across the bulk tissue is simply too weak to guarantee a massive, violent, local twitch response every single time.
They call it the voltage gap. The battery on paper is just too small to crank the engine in reality, and if the math doesn't work, the theory falls apart. So how did Kimura and Kobayashi resolve this? You can't just ignore the math.
You don't ignore the math, you correct the flawed assumptions underlying the math.
Okay.
Kimura and Kobayashi systematically dismantle the voltage gap by pointing out three fundamental errors the skeptics are making regarding biology, geometry, and physics.
Let's unpack those three flaws. Because if I am a skeptic, I am holding fast to that 15 to 20 millivolt threshold. What is the first assumption they get wrong?
Assumption number one, the skeptics are looking at the wrong nerve.
The wrong nerve.
They base their threshold on thick, heavily myelinated alpha motor neurons, which do require a massive jolt to fire. But modern neurophysiology has proven that the local twitch response isn't a direct hit on a motor neuron, it is a spinal reflex.
A spinal reflex. Explain how that changes the math.
It means the needle is actually triggering the highly sensitive, microscopic afferent-free nerve endings embedded in the fascia. These tiny sensory nerves have a significantly lower depolarization threshold than motor neurons.
Okay, that makes sense.
Furthermore, because these nerves are sitting in a highly inflamed, densified, mechanically stiff environment, they are subject to a phenomenon known in physics and biology as stochastic resonance.
Stochastic resonance, that sounds incredibly dense. Give me a tangible way to understand what that actually does to a nerve.
Imagine you're sitting in a completely silent room, and someone across the room drops a pin. The signal is so weak you might not hear it. It is below your threshold of perception.
Right.
Now imagine introducing a low-level random background noise into the room, like the hum of a fan. Surprisingly, that background noise floor actually elevates the weak signal of the pin drop, pushing it just over your threshold of perception. The noise helps you detect the signal.
Oh, wow. So the random static makes the system more sensitive to weak input.
Exactly. In the fascia, the 0.4 millivolt baseline field, the mechanical tension, and the inflammatory chemicals provide a continuous background hum. This stochastic resonance lowers the energy barrier required for the nerve to fire. You don't need 20 millivolts. The nerve is already balanced on a knife edge, hypersensitized by its environment. Even a tiny electrical fluctuation will push it over the edge.
That makes a lot of sense. The threshold isn't 20 millivolts. The threshold is functionally much lower because the nerve is already irritated. What is assumption number two?
Assumption number two is the most critical physics error. It is an error of geometry. The skeptics calculate the bulk tissue voltage. The average voltage is spread out evenly across a large, flat area of tissue. But the twitch doesn't happen across a large area. It happens exactly at the microscopic point where the needle touches the fascial plane.
Wait, I remember this from high school physics. If you have a highly charged object, the charge doesn't distribute evenly if the object is sharp. Like a lightning rod on top of a barn. It's a sharp point because electric fields concentrate exponentially at sharp geometries.
Exactly. It's a well-documented physical phenomenon called the tip field concentration effect. Think about the geometry of a medical needle. It's not a flat plate. The microscopic bevel of a needle tip has a radius of perhaps 10 to 25 micrometers. It is incredibly sharp.
Right.
When you introduce that sharp conductive point into an electrical field, the classical electrostatics of sharp conductors take over.
The needle acts as a lightning rod inside the tissue.
It does. The electric field does not remain uniform. It concentrates exponentially right at the extreme tip of the needle.
But wait, if I can play the skeptic for a second, the inside of the body is wet. It's fluid. Wouldn't the charge just instantly dissipate into the surrounding biological fluid? How can you have a concentrated electric field in a wet environment?
That is a great question, but remember stage 2 of the cascade. The needle isn't in a healthy fluid environment. It is piercing, stacking fascia.
Oh.
It is penetrating a thick layer of densified, dehydrated hyaluronic acid. The HA sludge is literally a dielectric insulator. The needle is acting as a highly charged electrode penetrating a non-conductive medium. The charge has nowhere to dissipate until it physically bridges the gap.
Oh, wow. The sludge actually allows the field to concentrate. So how much of an amplification are we talking about at the needle tip?
Mathematical modeling of this geometry shows an amplification factor of anywhere from 30 to 90 times the bulk voltage.
30 to 90 times.
Yes. So if the bulk tissue voltage under pressure is 25 millivolts, that means at the exact microscopic tip of the needle, the exact point where it is tucking the free nerve ending, that field is concentrated up to nearly 1 full volt.
1 volt, not millivolts, a whole volt. Inside human tissue at a microscopic point, that is an absolute lightning strike on a cellular level.
It is a massive, overwhelming localized charge. It makes the 15 millivolt threshold debate completely irrelevant. The bulk voltage doesn't pull the trigger, the concentrated tip voltage does.
That completely obliterates the voltage gap argument. But you said there were three flawed assumptions. What is the third?
The third assumption is that the needle itself is an electrically neutral, passive participant in the procedure. It is not.
Medical needles generate their own electricity.
They do, through friction. This is known as the triboelectric effect.
Like rubbing a balloon on your hair to create static electricity.
Precisely the same mechanism. In 2022, a researcher named Wu Yang conducted a fascinating study. They proved that when a standard stainless steel acupuncture needle is pushed, manipulated, and rotated through biological tissue, the sheer friction of the metal sliding against the tissue generates a localized triboelectric charge of up to plus or minus 6 volts.
6 volts, just from the physical friction of the metal entering the body.
Yes. Independent of any trapped capacitor energy in the fascia, the needle itself is dragging a massive electrical plow through the tissue. Furthermore, this intense localized field at the tip can cause a phenomenon called electroporation.
Electroporation, meaning it creates pores.
Yes. The intense electric field physically sources the lipid bilayer of nearby cell membranes to rip open temporarily, creating microscopic pores. This allows calcium ions to flood into the nerve instantly, triggering depolarization without even needing to activate the normal voltage-gated channels.
So, when you actually look at the real-world physics, the lowered threshold of an agitated nerve, the 90 times amplification of a lightning rod needle tip, and the 6-volt friction charge of sliding metal, there is no voltage gap. The needle is an absolute electrical powerhouse in that microenvironment.
Exactly. The math completely and elegantly supports the electrical model when you analyze it at the correct scale and in the correct context.
All right, this brings us to the clinical reality, the payoff. Because if you are listening to this right now and you have had chronic pain in your neck for a year, you want to know what this actually means for your treatment. How does understanding this battery in my shoulder change how a doctor fixes it?
It explains exactly why certain treatments work so miraculously fast and why they sometimes fail to last. We need to view the clinical intervention, whether it is ultrasound-guided fascial hydrorelease or advanced dry needling, through this new lens.
Yeah.
And to do that, we split the healing process into two distinct timescales: the immediate phase and the long-term phase.
Let's start with the immediate phase.
Yeah.
I come into the clinic, I have a stiff, agonizing knot. The doctor uses the ultrasound, spots the thick layer of stacking fascia between my muscles, and guides a needle right into it. What is happening in the first 5 to 10 seconds?
This immediate phase is what we call the spike and reset. Remember the architecture of your fascial capacitor. You have an upper layer of conductive collagen, a thick middle layer of insulating HA sludge holding a massive trapped electrical charge, and a bottom layer of conductive collagen.
Right. My biological multi-layer ceramic capacitor.
When the doctor inserts that highly conductive stainless steel needle and it pierces through those dense layers, the needle physically acts as a wire, bridging the gap between the separated conductive layers.
It connects the positive and negative terminals of the battery.
Exactly. It causes an instantaneous, catastrophic short circuit of the capacitor.
Phase 1, the spike.
Yes. The capacitor violently discharges all of its trapped, accumulated electrical energy at once. This massive, sudden spike of electricity instantly overwhelms the local afferent free nerve endings. They fire a massive distress signal up to your spinal cord, and your spinal cord reflexively fires the signal right back down to the motor neurons, telling the muscle to violently contract to protect itself.
Bam. The local twitch response. So, the twitch isn't the needle hitting a broken motor end plate. The twitch is the muscle reacting to a literal lightning bolt of discharged static electricity inside the fascia.
Correct. But here is the critical part for the patient's relief. Phase 2, the reset.
What happens the millisecond after that spike?
The capacitor is empty. That quasi-steady electrical field that had been building up for weeks or months, the electrical field that was constantly agonizing those free nerve endings and keeping your pain sensors firing 24 hours a day, drops to zero instantly. The battery is dead. The electrical torture stops.
And that is why patients feel immediate, seemingly magical symptom relief. I have watched videos of these procedures. A patient walks in unable to turn their neck. The doctor does the hydrorelease, the muscle twitches, and 5 seconds later, the patient is looking over their shoulder, crying because the deep ache is just gone.
It perfectly explains the speed of the relief. Think about it. It cannot be pharmacological. If a doctor injects a numbing agent or a steroid, it takes minutes or even hours for the fluid to diffuse through the tissue and bind to chemical receptors.
Right. Drugs take time to work.
And it cannot be purely mechanical fluid stretching, because injecting fluid also takes time to spread and stabilize the tissue mechanics. The only physiological mechanism in the human body that operates fast enough to provide instant second-to-second relief is electricity. You discharge the capacitor, the electrical field collapses, the nerve stops firing, the pain vanishes.
That is profound. But let's talk about the frustrating reality of chronic pain. We all know people who get dry needled, they feel amazing for a day or two, and then the exact same knot comes right back. Why doesn't the immediate electrical reset always last?
Because an electrical reset does not instantly fix the underlying structural sludge. If that hyaluronic acid layer remains dehydrated, hyperaggregated, and sticky, the dielectric insulator is still intact. As soon as you go back to your desk and start moving again, the piezoelectric generation resumes, and because the insulator is still there, the capacitor just slowly charges back up over the next 48 hours.
The battery just recharges. This is where the long-term phase comes in. How do we destroy the battery permanently?
This connects the capacitor model to the previously established fascial memory reset hypothesis. The long-term phase relies on two things: hydration and mechanoepigenetic remodeling. This is why fascial hydrorelease is so powerful. The doctor isn't just poking the tissue with a dry needle. Immediately following the electrical discharge, they use the needle to inject a bolus of fluid, usually a simple saline or Ringer solution, directly into that fascial plane.
They flood the engine with fresh fluid.
Exactly. This fluid does two things. First, it mechanically washes out the accumulated inflammatory pain chemicals. But far more importantly, it physically rehydrates the ground substance. It forcefully pries those glued collagen layers apart and dissolves the sludgy HA, restoring the fluid glide of the environment.
And what does restoring that mechanical glide do to the cells?
Remember Pillar 5, the YAP and TAZ genetic switches. They're activated by physical stiffness. When you inject fluid and restore the physical glide, the mechanical stiffness vanishes. The tissue goes slack.
And when the stiffness vanishes, the integrins stop pulling on the cell nucleus.
Exactly. The mechanical tension drops, the nucleus relaxes, and the YAP and TAZ proteins are turned off. They exit the nucleus. The fasciocyte stops receiving the genetic command to overproduce the sludgy HA.
The cell literally forgets its chronic programming. It resets its genetic memory back to a healthy baseline.
Over the next few days to weeks, the cellular behavior normalizes. The cells stop pumping out sludge, the natural fluid glide is restored, and crucially, the electrical capacitor cannot physically rebuild itself because the dielectric insulator has been washed away and is no longer being manufactured. The tissue returns to being a nanosecond dissipator. That is how you achieve durable, long-term resolution of chronic myofascial pain.
It is such a beautiful, elegant system when you finally zoom out and see all the pieces working in harmony. You have the electrical discharge for the immediate, instant relief, followed by the fluid hydration and genetic reset for the long-term, durable cure. If we accept this model, and based on the convergence of evidence, it seems undeniable it fundamentally shifts the future of physical medicine.
It radically changes the therapeutic target. Under the old motor end plate model, doctors were trying to paralyze or numb the tissue. They used Botox to stop acetylcholine or prescribed muscle relaxers to depress the nervous system. They were fighting the downstream symptoms.
But if you understand the fascial capacitor model, you realize you don't need to paralyze a muscle to fix a knot.
No, you don't. You need to focus on restoring the biophysical environment. You need practitioners trained in high-resolution ultrasound who can visually locate these thickened, densified electrical capacitors. You need to short-circuit the trapped charge, mechanically break up the densification with fluid, and restore the independent glide between the fascial layers so the body's natural electricity can dissipate normally again. It moves the entire focus of pain management from muscle pharmacology to fascial biophysics.
So, to you, listening to this right now, I want you to remember this entire journey the next time you feel that stiff, agonizing tension in your neck or your back. Your body is not a crude mechanical machine made of ropes and pulleys. It is an incredibly dynamic piezoelectric liquid crystalline web. That stiffness you feel isn't just a tight muscle that needs to be stretched harder. It is trapped electrical energy suspended in a dehydrated gel. It is a biological battery that needs to be discharged and a frozen river that needs to flow again.
It is a paradigm shift that finally respects the true complexity and elegance of human tissue. As we wrap up this deep dive, I want to leave you with one final, deeply provocative thought to mull over, something that builds on this model, but ventures into the cutting edge of biology.
Lay it on me. What is the next frontier?
We established in immense detail today that your fascia is a biological semiconductor. It is capable of generating, storing, and transmitting massive electrical charges through its liquid crystalline matrix. But recent advancements in quantum biology are revealing that this exact same highly structured water, this fascial web, is also capable of transmitting something else. Biophotons.
Biophotons, as in actual physical particles of light.
Yes, ultra-weak photon emissions. We now know that our cells emit and absorb tiny particles of light, and they use this light to communicate with each other almost instantaneously across the body's fascial network. The healthy fascial web acts as a biological fiber optic cable.
Oh, wow. Okay.
So the provocative question is this: if healthy fascia is a translucent fiber optic network for light-based cellular communication, what happens to our internal light network when our fascia gets densified, dehydrated, and turns into sludgy, opaque electrical capacitors?
That fundamentally shifts how I understand my own body.
Could chronic physical tension, trauma, and postural dehydration literally be dimming the light-based communication system of our cells? Are we not just electrically charged by our chronic pain, but physically darkened by it?
From muscle knots to trapped electrical fields to the literal dimming of our internal light network, this is exactly why we do these deep dives. Remember how we started? I told you that stepping into the world of chronic pain was like looking at a broken X-ray machine. The diagnostic landscape was murky. But I think today, thanks to the incredible synthesis by Kimura and Kobayashi and the convergence of quantum physics, anatomy, and genetics, that X-ray is finally starting to clear up. That jagged, painful knot in your shoulder isn't a broken lever, it is a trapped spark. Stay curious.